See, now the topic is stability of the colloids. Now the topic is stability of the colloid. See, what is the stability of colloid means? From the date of manufacturing to the usage of that product by the customer, there is no change in the colloidal dispersion. See, good colloidal dispersion, nothing but there is no change from the manufacturing date to the usage of that product by the customer. See, the stability of colloidal dispersion is due to the Brownian motion. Instability, nothing but if there is a precipitation of colloids, then we can call it a unstable preparation of colloidal dispersion. Next one is the lyophilic colloids. Lyophilic colloids is stable due to the presence of solvent film. So due to the presence of solvent film, the lyophilic colloid is stable. Lyophilic colloid is Lyophobic colloid stability is due to the presence of negative charge. Due to the presence of negative charges, the lyophobic colloid is stable. Now, DLVO theory is there. Now, the DLVO theory that will explains how the lyophobic colloid is stable due to the presence of charge. How the charge that will make stabilization of lyophobic colloids can be explained by DLVO theory. See, DLVO theory proposed by four scientists: B. Darjagin, L. Landu. Next one is E. Virve and Overbeek. Hence, we can call it DLVO theory. See, the stability of lyophobic colloid, in aqueous suspensions, that is because of the balance between the electrostatic force of repulsion and van der Waals force of attraction. Because of the equal balance between this force of repulsion and force of attraction, the stability of lyophobic colloids will depends. See, the stability of colloidal dispersion particles that will purely depend upon the total potential energy. Total potential energy interaction, we can call it VT. See that VT that is purely depend upon the electrostatic force of attraction, nothing but van der Waals attraction. We are nothing but electrostatic repulsions. Okay. See, if the lyophobic colloid is stable, the stability is because of predominance of repulsive forces. Repulsive forces is responsible for the stability of lyophobic colloidal dispersion. If there is a attractive forces are predominant, then the unstable dispersion we people will get. So this is simple basic concept about that one. See, now this will indicates the Y line indicates potential energy, the X line indicates the interparticle distance. See, if I have kept particle 1 here, next one is particle 2 at this distance. See, here we have kept one particle here, second particle. See, at this distance, then what will happen means the particles that will exhibit primary minimum means at this distance, the particle will exhibit attractive forces. Because of the attraction, the lyophobic colloid will get precipitated. See, this is one particle, this is another particle. Their atomic orbitals are get overlap here, and potential energies get increases, and this particle may get aggregate. This is particle 1, this is particle 3 I have taken. Means I have increased the same particle, the distance between these two particles is this one. When at this distance, what is that exact distance? Nothing but at 3 to 4 angstrom, attraction is equals to repulsions. Both attraction and repulsions will become equal. Because of that equal attraction and repulsions, the particles may exhibit the Brownian motion. Okay. Hence, the system will get stability. The zeta potential is 50 microvolts. See, if this peak height is get increases, the stability of this system is get increases. So this thing we can call as a this distance we can call as a for 3 to 4 angstrom. Still, furthermore, if we have increased the distance like this, still if we have increased the distance, then what will happen means at this distance, the that is secondary minimum. The particles are get separated at 1000 to 2000 angstrom, 2000 angstrom. Then here attractions will be get predominant. Because of the predominant attraction, the particles may get aggregate. See, this concept can be used in the flocculation. For getting the flocculated suspension, we people use the secondary minimum effect. But in case of colloidal dispersion, we can use the net peak energy concept, that is zeta potential. In case of suspension, we can use the secondary minimum. See, this is the one particle, this is a one particle, this is second particle of lyophobic colloid. See, when we people have used the optimum concentration of electrolyte, these are the electrolytes, then the electrolytes that will neutralizes the repulsion between this positive charged lyophobic colloid and responsible for the stability of this lyophobic system. That is optimum concentration of electrolytes. This electrolyte will induce negative charge. Okay, this electrolyte negative charge on this particle. So hence negative charge, negative, it will get repulsion. Hence, because of that repulsion, the colloidal system is become stable. Now, in the second case, if you people have used the excess concentration of electrolyte, if you people have added excess concentration of electrolyte, then total charge present on the particle, lyophobic particle is get neutralized, then it will become unstable. See, the same concept can be used. Adding excess of electrolytes, the charge present on the particle is get neutralized. Then this concept at secondary minimum, we can get this phenomena. This phenomena can be we can observe in case of secondary minimum. The particles are get separated at 1000 to 2000 angstrom. Okay, attractions are get predominant and the particles may get aggregate, that is used in controlled flocculation, means formation of flocculated suspension. Next, if you people have used a positive charged electrolyte, then that positive charged electrolyte that will form bond with negative charged one and that can withdraw from the lyophobic particles. Once now the formation of precipitate of positive and negative charged colloid, positive and negative charged electrolytes here. When the electrolytes, negative charged electrolytes removed from the lyophobic colloid, now the particles, lyophobic particles are get precipitated. So that thereby lyophobic colloid will become unstable. Next, last concept, if you people have remove the electrolytes, then what will happen? This is a one lyophobic colloid, this is another lyophobic colloid. Then the atomic orbital of one lyophobic colloid that can be penetrated into the atomic orbital of another lyophobic colloid. So atomic orbitals may get overlap, potential energy get increases, finally aggregation of the colloidal dispersion will be there. So this is about the instability of lyophobic colloid, that is by removal of electrolyte, by adding excess electrolyte and by adding the opposite charge to the electrolytes. Next one is RD Schulze rule. Next one is RD. Next one is RD Schulze rule. See, this rule can be used for only for the lyophobic salt. See, what is this rule will tell means, see, the coagulation power. See, if the greater the valency means valency is 3, aluminum valency is 3, barium is +2, valency of sodium is 1. See, if the valency of the electrolyte is more, then it can precipitate more amount of lyophobic colloids. Barium it can do precipitate only two lyophobic colloid. Sodium it can precipitate only one. Means see the valency, see the precipitation power of the electrolytes that is purely depends upon the valency. If the greater the valency, it can immediately make coagulation of lyophobic colloids. See, these are the red color things are the lyophobic colloids. So this is about the R.D. Schulze rule.